So this is basically the plot we just created. The solid blue curve there that's on the bottom, that's the curve we just generated. Okay, in terms of fraction of design load for vertical axis and story drift or story drift ratio on the horizontal axis. But there's a number of other curves here. So traditionally, if we were designing a frame like this by effective length method, at least traditionally in American practice, we would not have any notional load on the frame. And so it's a symmetrical structure, symmetrically loaded. So we load it up. If I'm plotting story drift versus load, there's no displacement. So it's just that vertical dotted curve that would be a traditional effective length method. But in 2005, AISC selected with the start of the direct analysis method. So if you're going to use an effective length method still, the worry, or what was clear, and one of the reasons to go to methods like the direct analysis method or comparable methods in Eurocode that don't have a stiffness reduction, but a larger notional load. The purpose of doing those is basically to have a better understanding of what's really happening in the structure. Now what's really happening in a structure like this is as we start to fail, we're starting to get a lot of bending of the frame, right? Now a traditional effective length solution, if you're designing your beams, life is good, I don't see any bending, I'm good, keep going. We'll do a column design, we've got an effective length factor or our buckling load of the column. The column strength curve is basically tied to the buckling load. So the column design works reasonably well. But with things like the beams, the connections to the beams, if we want to check, out of plane strength of the column, is that affected by the moment in the column? Well, the moment's quite a bit different in reality than the moment we calculated with the effective length method. So we're kind of missing all that. And and so the thought was, okay, it's very far from perfect, but for gravity-only load combinations, let's put on a notional load, let's require a notional load. So that at least gives the effect of some out of plumbness effects and what we might get in terms of generating moments in the frame. And it looks like that's, my guess is that's also the thought process behind your notional load. In the Indian standard, you're using 0.005 y sub I, so to speak, whereas we're using 0.002 y sub I in the Americas. So the dashed red curve is what we get, effective length method with a 0.002 notional load, or the 0.002 out of plumbness. Now, again, what is 0.002 coming from? Again, in the Americas, we're basically saying, or at least in the U.S., Canada's different. Canada's very different in many ways. The notional load, or that equivalent imperfection, that's tied to the Code of Standard Practice, and well, the largest out of plumbness that would be allowed before you might get hauled to court by the owner to fix it is basically 1 in 500. Okay, so that's that. But again, nominal stiffness. So you can see that curve is going a bit higher than what I showed you for the second order elastic curve in Mastan a minute ago. Okay, and then okay. Let me think here. Yes. All right. So the solid purple curve is the one we just generated, and the first circular symbol there on that curve is where we form the first plastic hinge. Gets a little flatter there. We form the second plastic hinge, and then we're going into post peak, where we've basically the frame is not going to be able to take any more load. Okay, so a couple of other curves here. bold solid green curve, that is obtained from what we can refer to as a distributed plasticity analysis. So what is that? It's a full nonlinear analysis. So we have defined representative residual stresses in all the steel members, and we track the spread of plasticity through all the members as everything is getting loaded up. Okay, and of course it also has geometric nonlinearity. So equilibrium, again, what is the mantra? First order elastic analysis is equilibrium in what? Dr. O'Rourke has the sign on his door. Second order analysis is equilibrium in what? Deformed geometry. Okay, first order analysis, oh, we're just doing it on the undeflected geometry. Okay, all right. So that the green curve, you could say, is the closest to the truth in the lab, but it's also done with a phi factor of 0.9 on Fy and a phi factor of 0.9 on E. And that's basically the Appendix 1 approach in AISC. If you're doing such of an analysis for a design evaluation, you would put the phi factors into the elastic modulus as well as on the yield strength. Okay, and then the last curve, the dashed blue curve. So from experience on this, I can tell you that for this frame, I think that a 0.9 stiffness reduction, which is basically what we use for the plastic zone on the elastic stiffness, is a better representation than a 0.8. So 0.8 is going to tend to be conservative on this particular frame. For other situations, that wouldn't necessarily be the case. So if I run it with a 0.9 stiffness reduction on elastic stiffness, I get the dashed blue curve, and yeah, you can see that, oh, that actually overshoots the distributed plasticity solution a little bit. And so what do we have going on here? Basically, okay, load versus lateral deflection. It's just a gravity load, but we're approaching a situation where, again, when we ran this with the reduced elastic stiffness, we're getting very close to a buckling load based on that reduced stiffness. So it's starting to deflect a lot. That's what the direct analysis method or these other notional load-based approaches in Eurocode are relying on. Is, okay, if we're not going to base our column stability, so to speak, on buckling analysis, well, all right, we're basing it on a geometric nonlinear load deflection solution. If we're getting close to the failure of the frame, the deflections are going to start to get large because of amplification. And so and that's physically, that's what's happening. If you're starting to collapse a structure, it doesn't collapse because, oops, suddenly it bifurcated. It collapses because, oh, I'm starting to get more and more bending, and now this thing is really moving. And it ends up failing with a lot of bending, right? So it's both a blessing and a curse. If you say, hey, I want to design based on what's really happening, okay, great, good. Okay, you've got a better feel for what's really happening. What's really happening can be a bit more complicated than what you're seeing when you run the analysis solution and do effective length method. If we look, so this is, again, a snapshot of what I showed you with the plastic hinge formations. The numbers are slightly different here, and the reason for that is just the round-off things going on where I converted from US units to SI units in running the problem. Question? Yeah. Is the battery not working?
Yeah, I was asking, effective length method is typically conservative because of the underestimation.
So the question is effective length typically conservative because of the underestimation? It can work either way, and we're going to see that the results for this frame are ending up being conservative. But we could create other problems where it goes the other way.
That comes from that is the K elastic?
So where does that conservatism come from? I've got some plots here that I think that can help we can talk through that. So let's look at some results here, and I think that can help with your question. It's exactly where I want to go next. And I actually skipped this here. The white dots on the effective length method here, these points. So those are actually where, if we're doing the so-called unity checks, the evaluation of the verification, we got to 1.0. That means we've reached the strength check. From elastic design, we don't allow any further load. So with the effective length method here is basically saying with the notional load in AISC, you can only get 80% of what we wanted to apply on this frame on the frame. Now, of course, our fancier second order inelastic solution is telling us we can get close to 20% more than the load that we were looking to design for. All right. So answering your question, I think we may be able to talk through a few things here with this. So this is the force point trace that I showed you that we did in Mastan. So we basically generated the lightweight solid purple curve here in Mastan. And if we're doing the strength check in Mastan, it's based on essentially PMP prime at the as an anchor point for the yield surface there on the horizontal axis. But another anchor point there is essentially the envelope of the forces at full plasticity on the cross section that we can get to. If it's just pure axial compression, okay, there it's 0.9 phi times py. So that's 3,825 kilonewtons. That's way up above the roof here. Okay, and so that's what that bold purple curve is. That's our yield surface that represents essentially the cross-section strength there at the top of that column. And so we're reaching capacity essentially when we reach that particular cross-section strength here. And so that's what you see is happening with the purple curve, the plastic hinge analysis. It hits that curve, and then we have to stay on the yield surface. We can move along the yield surface, but and so we continue to increase the moment, but the axial force is reducing. Now you can see also the way that is working for the case with the 0.9 on the elastic stiffness. Okay, yeah, I had to collect my thoughts on one thing here. So notice those points from the analysis from Mastan, they're slightly outside of that bold purple curve. The reason for that is the bold purple curve is the equations H1-1 from the beam column interaction equations in AISC. And so those are a good approximation of what we get from a strength for the cross section. Mastan is using a different approximation for that strength, which is a smooth curve or a smooth surface. And so that's why those points are outside. The Mastan's representation of the plastic strength at the plastic hinge is slightly different. And you can see the bold green curve. And okay, yeah, that's the plastic hinge model is tracking pretty close to what we get from the distributed plasticity or plastic zone solution. So now to your question, what's going on with the effective length method? So in the effective length method, instead we basically are protecting ourselves by saying, okay, if we could take the loads we've got and shift all the loading around, so we've got that same axial load on the column, and well, at what point, if I didn't have any moment, would I fail in axial compression? And so we get an elastic buckling solution for the side sway buckling of the frame. We get a column strength for pure axial compression. So we get an anchor point. We say, oh, well, that's our anchor point for pure axial compression. So what's that representing? That's representing again, oh, if I had pure axial compression, just say put loads over the tops of all the columns, push it down, and I get to a point where the frame is, where I say, oh, I lost my column capacity, it goes. That's kind of more of a bifurcation problem. And then the approach with effective length method is saying, okay, oh, we're going to use that as an anchor point. Now let's look at the other anchor point. If I didn't have any axial compression, let me just apply the moments. Oh, when would it fail in bending? Oh, here it fails at MP prime, just slightly less than MP because it's semi-compact. Okay? And then we say, okay, we're going to create a strength interaction curve between those two anchor points. And in the American practice, we use a very simplistic curve, this bilinear dashed red curve that you see here for that. So that's the approach. And then you can see from our solution here, when traditionally the very light red solution, when there's no notional load, we hit we intersect that curve with the force point trace in our column. Okay, we're done. It's elastic design. We don't go beyond reaching the capacity of the most critically loaded member. Okay? And with the notional load on here, it's a little bit smaller because of the notional load effects. So it's kind of a bit rambling to explain what's going on with that, but that's what that's doing, right? And we say that we're trying to use that to approximate what would this frame do. It's clearly not reality. What's closer to reality is we had an out of plumbness in the frame. As we're starting to approach a strength condition, we're starting to get a lot of lateral movement, a lot of bending in the frame. That's how it fails. Okay, so that's what the direct analysis method curve or the plastic zone analysis curve here are doing. Does that help? Okay, all right, good. So any other questions here? That's basic question pretty much drove to the heart of where I wanted to try to wrap up here with this discussion. All right. Now, just to highlight one more thing there, you can see I have labeled VCPN parentheses KL. So we can get our elastic buckling load of the exterior column here. That's what is the force in that column at theoretical elastic buckling of the frame. And we can back calculate a K factor from that, right? We equate pi squared EI divided by K2L squared to that buckling load. We calculate K. The K factor here is larger than 4. Why is it so large? Because we have two exterior columns that are providing the lateral load resistance. We have 4 interior columns that are carrying a lot of the vertical load. Those are not helping at all. In fact, when we deflect laterally, we get P delta effects that are destabilizing the rest of the frame. So in a buckling solution, that causes the effective length factor to get large on the exterior columns. Make sense? All right. So now, is this okay? Well, what you can see is happening is with the graphic I just pulled up here, the direct analysis solution would give us 46% more strength. Okay? And if we did this more in the form of the way Eurocode would do it, rather than having a stiffness reduction, here it's a 0.8 stiffness reduction, all the elastic stiffnesses, the Eurocode would use a larger notional lateral load, and so that would tend to give larger lateral moment. if everything is working perfectly, we get about the same result either way. So in the Americas, a reduced stiffness with a notional load that's, or an out-of-plumbness that's more representative of what you would tolerate. In Europe, a larger notional load or a larger imperfection that's increased to try to capture the aspect that, oh, I'm going to get a larger bending effect as I start to approach a strength condition. And using either of those approaches, the alternates to effective length method, you say, oh yeah, okay, we can, in terms of column strength here, we're getting 46% more strength out of that column. All right, you don't get something for nothing. If you're going that far, you're basically, so we didn't take it that far because we stopped, remember the load we want to design for was 1.0, and this is taking it to, what do we get, essentially 1.16, so 16% larger load than what we were designing this frame for. And if we took it all the way out to that capacity, the moment that we have at the top of the column, which is also the moment we have in the roof girder, it's the moment in the connection between the column and the roof girder, the moment we have to design the column for out-of-plane lateral torsional buckling, 133% larger. So that's 100 plus 133%. Okay, and it's not. The first plastic hinge is actually way over there, over the top of the first interior column in the girder. Okay.
So that's the intersection point, first point, right?
That's the first plastic hinge, and we're plotting the behavior at this second plastic hinge, where the second plastic hinge occurs.
At the leeward column.
At the leeward column,
Okay. So in direct analysis method, although we are not explicitly talking about the plastic hinges, but indirectly relying on the plastic hinge capacities.
Yeah, I'm kind of glossing over a lot of things. Again, as I said yesterday, my aim was to go relatively light with direct analysis method, but kind of tie it in with Eurocode, and so I've just made the comments about that. Sorry, I lost my train of thought. Tell me your question again.
So we are not explicitly talking about plastic hinges in the direct analysis method, but indirectly relying
yes.
on that.
Yes. So if we go to Appendix 1 of the AISC specification, then Appendix 1 basically says, okay, everything we're doing with the direct analysis, here's how you do it with plastic hinges. Okay? And so Appendix 1 basically goes that next step to a second order inelastic analysis, or also says, and if you want to do a plastic zone solution and use that for the design, here's how you do that.
Distributed plasticity.
Yeah, right. Pretty much a 0.9 phi factor on yield, a 0.9 phi factor on the elastic stiffnesses, and then as a judgment call, if you're running a plastic hinge-based solution, is that good enough to call it, oh, I'm capturing all the effects or not? The intent in Appendix 1 would be you'd use a 0.8 with the plastic hinge-based solution.
Okay.
Yeah.
Thank you.
Yes, everything up to this point, we were just talking about elastic design, and then I took it a few steps further here to say, okay, we tied it in with a plastic hinge formation to evaluate the capacity of the frame. So this is a graphic to try to maybe get closure and make sense out of, is effective length method okay? We've been designing for that since the beginning of time, and things aren't falling down. It's generally okay, but what's going on? So if we compare the two approaches, and you could say direct analysis method, the Eurocode approaches that do not do a stiffness reduction are analogous to what we're talking about here with direct analysis method. So in both of these approaches, we're essentially using the same beam column strength interaction curve. But with the effective length method, our anchor point for the axial term is based on a buckling solution. In direct analysis method, it depends. The routine application of direct analysis method, we calculate the column capacity based on K equals 1, essentially a braced buckling strength. You could use K less than 1, but the argument was we're doing direct analysis to try to not have to calculate an effective length factor, so please don't tell us to do direct analysis and then calculate one. What I just showed you in the approach we took for this particular frame, I showed you yesterday that we were justified to take phi pn equals to phi py, the 0.9 times the yield capacity for the axial term. So that's what we were based on. So that allows us to very nicely, or very makes for an easier discussion of, okay, yeah, our strength here in the plastic hinge solution was essentially tied very much to the cross-section strength at the top of that column. But routine practice, we use KL equals L, and the reason for that is to cover the bases. If we have a very light column somewhere in the building that's failing in a non-sway mode, we want to make sure that we don't miss that. Then what are the differences? Well, in the effective length method, we get a second order elastic response that's based on the nominally elastic structure, and with if it's a gravity load only combination, we have a notional load, but otherwise it's nominally elastic and perfect geometry. The actual response, of course, is one where the frame, like the one we just looked at, had initial out of plumbness and had the inelastic effects, the stiffness reduction effects. So the solid black curve there kind of represents, okay, that's what we would expect. And so as the real response, you say, okay, well, the two are not the same, but if everything is working the way we would hope, if we're thinking of capacity basically, or the amount of axial force we can develop in the columns as representing capacity, the vertical axis here for P, if things are working the way we would hope, we get to essentially the same level of P as the actual response when we're doing the effective length method. You can see that with the example we just had, if we go back, we were conservative. Now with the direct analysis method, again, this is where I say the direct analysis method is a poor person's test simulation. Saying, hey, I really don't have the time or the capabilities to do a distributed plasticity full nonlinear analysis. I'm trying to design this frame and my phi isn't that big. Okay, but can I do something that's fairly coarse that gives me a representation of coarse representation of what's really in the structure, what's really going on. So that's the attempt with the more recent alternative methods, direct analysis or comparable methods in the Eurocodes, trying to match that actual response. And so you could say that in that context, both methods are legitimate. The direct analysis method tends to be more accurate as long as you have an accurate second order analysis. So you need requirements to try to ensure that. The effective length method needs additional restrictions to guard against its limited ability to represent the actual internal forces. And so in the AISC practice, the restrictions are we need to put on a notional lateral load for gravity-only load combinations. I see the Indian code also does that with a 0.005. And in the AISC practice, if you're designing by effective length method and your B2, or your ratio of your second order lateral displacement to first order lateral displacement, is greater than 1.5, then you say, okay, oops, the code tells me I'm not allowed to use effective length method. I have to go to the direct analysis method to do the solution. The reason for that is, you can say that, well, wait a minute, my design was conservative for this frame we just checked. And, oh, yes, our B2 was much larger than 1.5, so by the code, effective length method would not be allowed. You say, wait a minute, it was conservative, it was okay. It's okay, yeah, it's basically saying, yeah, but we don't know when it might go the other way. So, or it's hard to determine that, so we're going to restrict it.